Hi, I'm Min Song Cai, a graduate student in CPAS. I will give a presentation of my work on the transformer design for the 48 volt to 12 volt bus converter. 48 volt to 12 volt intermediate bus converters has wide applications. They are used in aerospace and military, wireless network, server and computing, and telecommunications. The state-of-art 48-volt regulated isolated bus converters are shown in the figure. We can see most of them have low power ratings and limited power density. Our goal is to design a 1 kilowatt bus converter with 96% efficiency and power density higher than 550 watt per cubic inch. This is the proposed two-stage architecture for the bus converter. The first stage is a four-phase buck converter running at 500 kHz per phase. The first stage is used as regulation stage. The second stage is a LLC converter for isolation. It functions as a DC transformer with 3:1 voltage ratio. The two-stage architecture benefits from the simple control of buck converter, and LLC DCX always works at optimal efficiency. However, at high switching frequency, the transformer design and optimization becomes a major challenge. The work is focused on the LLC transformer. Here shows the basic structure of the transformer. The 3-to-1 transformer is broken down into three 1-to-1 transformers. The primary windings are connected in series, and the secondary windings are connected in parallel. This distributed transformer design reduces the large conduction loss on the secondary side and at the same time naturally guarantees the current sharing between the transformers and SR devices. This design uses 14-layer PCB, with top and bottom layers for devices and the middle 12 layers for windings. The windings are perfectly interleaved and are arranged in a symmetrical order. This alternating MMF structure achieves better current sharing for parallel layers. The top view shows the SRs and output capacitors. We integrate them with the transformer so that the secondary termination loss is minimized. This figure shows the secondary winding and the current path. We improve this structure by merge the secondary winding with the same VO terminals. This reduced the winding loss by 40% due to better interleaving. Another improvement is on the primary winding termination. Here we show the traditional non-interleaved termination and via structure. The two terminations of windings are placed side by side. If we take a look at the current flow, we notice that the termination and via current are not interleaved, and this will cause large current crowding. In the proposed design, by implementing a finger-shaped structure, we interleave both the termination and vias. So we can see the current in the termination and the current in the vias are interleaved. And with this structure, we achieve 50% termination loss reduction. With all the improvement and final optimization of the transformer, we have the prototype. The test efficiency is shown in the figure. It achieves 97.8% peak efficiency, and the thermal performance is good at both mid-load and full load. This is the LLC converter. These are the primary side devices. These two are the half-bridge gate drivers. And in the middle, we can see three transformers. And then we will put the cores. And these are the SRs And here we have the isolators and the SR drivers. And these are the cores we use. So we integrated the 3 transformers, and then we put the cores on the board, and we have this finished board. This is the waveform of the LLC converter. The first waveform is the primary side device VDS. The second blue waveform is the resonant current, and the bottom waveform is the SR VDS. So first we can see the current is a complete sine waveform, which means we are operating at the optimal point of switching frequency equal resonant frequency. And this is one of the benefits of the DCX. We can always operating at this point. And for the primary device VDS, we can see the VDS drop to 0 during the dead time. The magnetizing current discharged the COSS. And for the SR VDS, we can see the similar waveform, which means we achieve ZVS for both primary and secondary devices. And here we show the full load waveform. And this is the waveform at 40 amp. And this is the waveform at 10 amp. So we can see these 3 waveforms are very similar, and the ZVS can be achieved even at light load. Thank you for watching the video.